Welcome back to The Explainer. Today, we're diving into a terrifying mid-air mystery that completely redefined our understanding of aviation safety. It turns out, to really understand what went wrong, we have to look way past the cockpit doors and peer straight into the microscopic science of fuel contamination. We're examining the harrowing case of Cathay Pacific Flight 780, a flight that suddenly and inexplicably just lost its ability to stay in the sky.
Picture this. It's April 13th, 2010. A massive 200-ton Airbus A330 carrying 309 passengers and crew is cruising high above the rough, choppy waters of the South China Sea. Everything seems totally normal, and then suddenly the pilots are forced to make a chilling radio call. Both of their incredibly powerful Rolls-Royce Trent 700 engines have failed. They are, for all intents and purposes, flying a 200-ton glider over the ocean.
Okay, let's dive into this, because the answer to what brought this massive feat of engineering to its knees wasn't a mechanical explosion, and it wasn't a bird strike, it was a microscopic powder. How on earth can something smaller than a grain of sand cripple a state-of-the-art commercial airliner? Well, to understand the science, we first need to look at the symptoms.
Section 1. This symptom: dual engine failure.
Captain Malcolm Waters and First Officer David Hayhoe were cruising perfectly normally from Surabaya, Indonesia to Hong Kong until a sudden bang shook the entire airframe. Let's track how this builds, because the timeline is literally terrifying. First, a warning pops up for engine 2. The captain pulls it back to idle. But then, engine 1 begins to stall out. Within moments, both engines are still physically running, but producing absolutely zero thrust. They are dropping out of the sky at a rate of 1,300 feet per minute.
Section 2. The autopsy, investigating the valves. To figure out why this happened, investigators had to perform a digital autopsy on the aircraft's flight data. And this brilliantly illustrates the core of the problem, because the flight data pointed them straight to a highly critical yet rarely discussed component: the main metering valve. Think of this valve as the heartbeat of the engine's power. It's a precisely machined piston inside a cylinder. When the pilot pushes the thrust lever forward, this valve slides open to let more fuel into the engine. Pull the lever back, it slides closed. But on Flight 780, the flight data showed the pilots moving the levers desperately, but the fuel flow was remaining completely flat. The valves were stuck.
When investigators in the UK took a saw and physically cut the jammed valve in half to see what was inside, they didn't find broken, sheared metal like you might expect from a mechanical failure. Instead, they found the incredibly tight tolerances of the valve were completely choked by this strange, sludgy white powder. It was incredibly fine, finer than castor sugar, and it had literally glued the valve shut.
Section 3. The pathogen: superabsorbent polymers. Investigators isolated this mechanical pathogen using a high-powered electron microscope and X-ray spectroscopy. What looked like a simple white powder to the naked eye was actually millions of tiny, perfectly round spheres lodged deep within the metal components.
The chemical analysis revealed that these spheres were superabsorbent polymers, or SAP. And here is the incredible irony of this whole situation. SAP is actually a safety measure. It's an inorganic compound used inside the filter monitors of airport refueling trucks. Its entire job is to chemically bind with any stray freshwater in the aviation fuel, expanding into a harmless gel that gets trapped in the filter, keeping the water out of the airplane's tanks.
If you've ever looked out an airport window and seen those refueling trucks driving around, they use this normal filtration. The SAP absorbs the water, forms a gel, and stays safely trapped inside the truck's filter fibers. But on Flight 780, that system completely broke down. The filter structurally failed, releasing these microscopic SAP spheres directly into the 24,000 liters of jet fuel that were pumped into the Airbus. But why on earth did the filter break in the first place?
Section 4. The catalyst: the saltwater reaction. To find out what caused this, investigators tracked down the specific fuel truck over at Surabaya Airport. When they opened up the truck's filtration system, they were shocked. The filter wasn't just slightly damaged, it was totally crushed and collapsed inward.
When they dissected the layers of that collapsed filter, they found a microscopic clue that blew the case wide open. Right alongside the SAP spheres, they found a coating of sodium crystals: salt. Finding salt inside an aviation fuel system is incredibly abnormal. Jet fuel and fresh water do not have salt in them. This meant that salt water had somehow violently breached the entire system.
So, the crucial point is this. Investigators discovered that the underground fuel hydrants at Surabaya Airport were undergoing some construction and had accidentally been exposed to salty groundwater.
When this salt water was pumped into the truck at high pressure, the chemistry of the SAP totally failed. The sodium in the salt water essentially blocked the SAP from forming a stable gel. Instead of becoming harmless and trapped, the SAP spheres just remained loose. The filter core then collapsed under the pressure, and millions of these loose spheres flooded into Flight 780's tanks, eventually migrating all the way up to the engines and jamming those critical main metering valves. It was a perfect microscopic storm.
Section 5. The aftermath, a high-speed miracle. Now let's bring this microscopic science back to the very real human stakes in the cockpit. The pilots are staring down the South China Sea, actively preparing to ditch the aircraft in the water, which is an incredibly dangerous maneuver.
Captain Waters had an idea based purely on mechanical intuition. He realized that rapid, panicked movements of the thrust lever were doing absolutely nothing. So he began engaging in a slow, agonizing physical fight against that sap sludge. He started manipulating the thrust lever for engine 1, millimeter by millimeter. By moving it incredibly slowly, he was able to forcefully squeeze just enough fuel past those sticky sap spheres to get the engine rotation to slowly, finally increase.
Through sheer finesse, he managed to coax engine 1 all the way up to 74% thrust. This was just enough power to keep them in the air and get them to Hong Kong Airport. But here is the terrifying scientific catch. Because the sap had jammed the valve so badly, when he tried to pull the throttle back to idle for the actual landing, the valve wouldn't close. Engine 1 was now permanently stuck wide open at 74% thrust. So they were coming in hot, very hot. The aircraft touched down at 230 knots. To put that in perspective, that is 100 knots faster than a normal landing. Because one engine was still producing massive forward thrust and they only had one working thrust reverser, the pilots had to apply maximum violent braking. They burned through almost the entire 12,500-foot runway. The friction was so intense that the brakes hit a staggering 1,000 degrees Celsius, sparking a severe fire risk and forcing an immediate emergency evacuation right there on the runway. Amazingly, everyone survived, and the pilots rightfully received the prestigious Polaris Award for their incredible airmanship.
The legacy of Flight 780 is a profound shift in aviation science. It triggered a global mandate to totally redesign fuel filter monitors, removing SAFT technology entirely from aviation fuel systems worldwide to prevent this exact chemical chain reaction from ever happening again. It leaves us with a fascinating yet slightly chilling thought. Next time you board a flight, remember that in an industry dominated by massive engines and highly advanced computers, safety sometimes comes down to battling invisible, microscopic vulnerabilities hiding just out of sight, just waiting for the perfect storm. What other tiny threats are out there, waiting to challenge our grandest engineering?